Good morning, students. Welcome to online classes AB and PRR College Core. I am Srinivas, your physics lecturer. In the last video, we discussed about the syllabus. We are having 5 units, and I am going to discuss about Unit 3, Unit 4, and Unit 5. Today, I am going to discuss about the Unit 3 chapters. There are two chapters in Unit 3. The first chapter is Solar Energy. The title of the chapter is Solar Energy. So, let me give you the introduction of solar energy. As we know, sun is the primary source of the solar energy. We'll get the radiation from the sun. So this is the primary source. The solar energy will get mainly from the sun. And we are having so many members of the solar system. And one among them is the sun. And sun is the largest member of our solar system. And the heat comes out from the sun, from the core of the sun. Actually, the sun is having three parts, namely corona and chromosphere and photosphere. So the central portion of the sun is called core or photosphere. The heat comes out from the core of the sun, and there some reactions are taking place. Those reactions are called fusion reactions. So heat comes out from the sun due to some fusion reactions that takes place in the core, and the energy coming from the sun is radiated to the earth in the form of some waves. Those waves are called electromagnetic waves. So the whole radiation from the sun is like electromagnetic waves, and the amount of energy received from the sun is generally 2.8 into 10 power 23 kilowatts. That is called the output of the sun. How much heat the sun delivers, that is called the output of the sun. That is nearly 2.8 into 10 power 23 kilowatts. And the energy reaching the earth. So the complete output of the sun cannot reach the earth. There are some obstructions. Some sun energy will be radiated, diffused like that. So only some part of the energy emitted by the sun will reach to the earth. So generally the energy reaching the earth is nearly around 1.5 into 10 power 18 kilowatt hour per year. So if we can take it at an average in 1 year, so the amount of energy reaching the earth is generally 1.5 into 10 power 18. So this is generally about the solar energy, the introduction. Then how can we utilize the solar energy? There are two methods. In order to utilize the solar energy, there are two methods, namely direct methods and indirect methods. In the direct methods, there are two processes, namely thermal and photovoltaic. And in the case of thermal method, so here we'll collect the radiant heat from the sun and using it in a thermal system. So we'll collect the energy from the sun, then we will use it in a thermal system. So that's why it is called solar thermal system. And second one is photovoltaic system, or otherwise it is also called as solar PV system. Here what we'll do is that we'll collect and converting it directly into electrical energy. So we'll collect the solar energy and we'll convert it into electrical energy by using some photovoltaic systems. There are some systems which can be used to convert the energy received from the sun into electrical energy. So that is called photovoltaic system. So that's why this method or this system or this process is known as solar photovoltaic system. So that's why these two methods, that means the solar thermal system and solar photovoltaic system, these two methods comes under direct methods of utilization of solar energy. And there are indirect methods. In the indirect methods, we will convert the solar energy into different ways. So that's why here we cannot extract directly the sun heat and will convert it into other forms. So that's why here these are called indirect methods, and they are hydropower, wind, biomass, ocean energy. So these are all the indirect methods of utilization of the solar energy. Then the advantages of solar energy. What is the use of solar energy? You see here the advantages are, it is a natural source. You see, solar energy is a natural source. The radiation is emitted by the sun naturally. So the God given us that. So directly the sun is radiating, that is a natural source. Sun is a natural source and it is available freely. We can't spend anything for it. So it is available freely in the nature. And the second one is it is available in plenty. So much of solar energy we can receive it. So that's why it is available so much. So that's why it is called, it is available in plenty. And it is non-polluting. So it cannot create any pollution to the atmosphere. So it is non-polluting. And no need of destruction of the forests. Actually, you see, in order to get the fossil fuels and in order to get the wood, deforest the we have to deforest. That means we have to cut the trees and we have to destroy the ecosystems. But in the case of solar energy, the main advantage is that there is no need of destruction of the forests. So those are the advantages of solar energy. Then the disadvantages. So the main disadvantage is the solar energy depends on the change in the climate, seasons, weather. You see here, when the seasons changes, when the weather changes, we can't get the whole solar energy from the sun. So that's why whenever the atmosphere is cloudy, we can't get much solar energy. And when it is very hot, then we can get more solar energy. So that's why it depends upon change in seasons and weather. And the disadvantage is it must require high initial investment. In order to get the solar energy, actually, we have to construct some solar cells and some solar panels. So for that, we have to invest more. So that's why the disadvantage of solar energy is we must require high initial investment. We have to invest high initially, and the solar panels are usually bulky. They are large in size, they are somewhat robust, they can't be transportable. So that's why solar panels are usually bulky. And the disadvantage and other disadvantage is that the solar systems generally does not work at night. Of course, we can use the solar systems by connecting to the batteries. If we can connect it to the batteries, then we can make use of those batteries and we can get the solar energy at the night also. But generally, the solar systems generally does not work at night. So we can't use it in the night time directly. So those are the disadvantages of the solar energy. Then let us go to another topic. What is meant by solar radiation and the spectral power distribution of solar radiation? So solar radiation. Generally, the radiation coming from the sun is called solar radiation. So if we can consider this radiation, it will occupy so much region. That means if we can consider its frequency of the radiation or wavelength of the radiation, it will occupy so much range. It is of wide range and it is emitted in the form of electromagnetic waves. So that's why the solar radiation is the total frequency spectrum. It is like a spectrum. It covers both visible and invisible radiation or invisible light. So that's why it can occupy wide range of frequency range, and these are called electromagnetic waves. And this will cover generally visible light region and invisible light region. So in order to explain the spectral power distribution of solar radiation, we must know there are two types of radiations, namely extraterrestrial radiation and terrestrial radiation. So what is meant by extraterrestrial radiation? Generally, up to some height only from the earth, if we can go to a certain height, there is atmosphere. If we can go beyond that, there will be no atmosphere. So that's why the solar radiation incident on the outer atmosphere of the earth. So beyond certain level, so how much radiation is incident on the earth above the atmospheric layer, so that is called extraterrestrial radiation. So solar radiation incident on the outer atmosphere of the earth is called extraterrestrial radiation. And how can we define it? Means, you see, if you can take a plate having area 1 into 1 meter square, if we can keep this plate at Earth's outer atmosphere, how much energy is incident on it? So that amount of energy itself is called extraterrestrial radiation. So that's why we can define the extraterrestrial radiation like this. It is the energy on 1 by 1 meter square plate placed at Earth's outer atmosphere. And you see, the extraterrestrial radiation is above the atmosphere of the Earth, so it is not affected by changes in atmospheric conditions. Even though there is a change in atmospheric condition, so there is no effect on the extraterrestrial radiation. And generally the extraterrestrial radiation, if we can consider it as a spectrum, and it contains, generally it occupies 8% of UV radiation, 46% of visible light, and the remaining 46% of infrared radiation. So it contains, you see, it is occupying UV radiation, it is in the range of visible light, and again it is in the range of infrared radiation also. Then we'll go to next radiation, that is terrestrial radiation. You see, terrestrial is a word related to the earth. How much radiation is there on the earth, that is called terrestrial radiation. So that's why it is the radiation incident on the earth's surface. How much radiation is incident on the earth's surface, that is called terrestrial radiation. Generally, when the radiation enters into the atmosphere of the earth, then the total radiation cannot be received by the earth. Some of the radiation will be lost. So the energy lost is due to absorption, scattering, diffusion, and reflection. Generally, by these four processes, some energy will be lost. We see absorption. Generally, this absorption occurs due to the presence of water vapors and ozone in the atmosphere. In the atmosphere, you see, some water vapors are present. So these water vapors absorb some radiation of the earth. So that's why, due to this absorption, some solar energy is lost. And the second one is scattering. The atmosphere contains some particles. So when the light rays collide with these particles, which is present in the atmosphere, what will happen? The scattered radiation is redistributed in all directions. Whenever the sunlight is colliding the particles of the atmosphere, the sunlight will be scattered in all directions. Due to this also, some solar energy will be lost. And third one is diffusion. Generally, the light rays are diffused because of clouds. Whenever the clouds are present, some radiation is diffused from the clouds. And the last one is due to reflection. Some radiation is reflected by the Earth's surface also. Total radiation cannot be absorbed by the Earth. Some of the radiation will be reflected by the Earth's surface also. So that's why there are four factors which will affect the solar energy. So that's why the 100% of solar energy that is coming from the sun cannot be reaching the earth because of these four factors. Now you see, here is a diagram. In the diagram, you see, there is a boundary. You see here, there is a dotted line. So this dotted line shows the upper limit of the atmosphere. Above that, extraterrestrial region is there, and below that, terrestrial radiation is there. You see, the energy received from the sun is lost due to so many factors. You see here, 6% of the radiation is scattered by the atmosphere. And again, you see here, 20% of the scattered light is reflected by clouds. And again, you see here, 19% absorbed by the atmosphere and clouds. And here you see 4% is reflected by the surface of the earth. So only the remaining 51% of the radiation is absorbed by the earth. So the total radiation is not absorbed by the earth. Some of the radiation is lost due to scattering and reflection and absorption. So like this, so much radiation is lost. So this is about extraterrestrial radiation and terrestrial radiation. Then we'll move to another topic, namely spectral distribution of solar radiation. How the solar radiation can be distributed, we can show it in a graphical way. Here you see in the graph there are two curves. So first one is about extraterrestrial radiation curve, and second one is terrestrial radiation curve. You see here, I'm showing with an arrow. This curve represents the extraterrestrial radiation curve. And the second one, you see here, this one shows the terrestrial radiation curve. So on the x-axis we have taken wavelength, and on the y-axis we have taken the distribution of the solar radiation, that is in micrometers, that will be taken on the y-axis. Now you see there are two curves. One first curve is the above curve is for extraterrestrial radiation, and the below curve is for terrestrial radiation. And first I will try to explain you how the wavelength range will be there for all the rays or waves. I will tell you about the electromagnetic spectrum, the wavelength range I want to tell you. The gamma rays is in the wavelength range of 10 power minus 6 nanometer to 10 power minus 2 nanometer. The X-rays 10 power minus 2 nanometer to 10 nanometer. The ultraviolet radiation will occupy the wavelength range of 10 nanometer to 100 nanometer. Similarly, the visible radiation, what we will see, that radiation will occupy the wavelength range of 100 nanometer to 10 cube nanometer. 10 cube nanometer means 1 micrometer. And the infrared radiation occupies 10 cube nanometer to 1000 micrometer. Similarly, the microwaves will occupy 1000 micrometer to 10 centimeter. And finally, the radio waves will occupy 10 centimeter to 100 kilometers. This is the actually electromagnetic spectrum. How these visible and invisible radiation will occupy the wavelength range, that is the wavelength range for the electromagnetic spectrum. Now you see from the graphs what we can observe is that the solar radiation covers the spectrum of electromagnetic radiation. The solar radiation covers the spectrum of electromagnetic radiation in a wide range of frequencies. Just I told you that from starting to ending, from gamma rays to radio waves, so much range of frequency range is there. So the solar radiation will cover all this frequency range or wavelength range. And in the case of extraterrestrial radiation, the wavelength range is 0.2 to 4 micrometer. You see from the graph here, you see this is 0. This is 1. If you can see the above graph, first graph, top one, that will occupy. So this graph, this will occupy. See up to here, it is so much curve will be there. So up to here, it will occupy. Generally, it is from 0.2 to 4 micrometer. If you can see here generally it will be 4 like that. So 99% of the extraterrestrial radiation is in the wavelength range of 0.2 to 4 micrometer. And you see here the maximum intensity here. This is the maximum intensity. If you can see that on the x-axis, how much is value generally nearly 0.5. That means if we can say it exactly, it is 0.48 micrometer. So maximum spectral intensity. So this is the maximum spectral intensity. Here its value is nearly 0.5. So exactly if you can speak it, it is 0.48 micrometer. And this extraterrestrial radiation is generally 6.4% of extraterrestrial radiation is in the UV region, ultraviolet region. If you can see that frequency range of ultraviolet region, so the 6.4% of the extraterrestrial radiation is in the UV region and 48% is in the visible region and the remaining 45.6% is in the infrared region. So generally, complete absorption of the shortwave radiation is in the range of 0.29 micrometer to 2.3 micrometer. If you can see these areas, you see here, this is the area occupied by the terrestrial radiation, and above one, this area, complete area, will occupy the extraterrestrial radiation. So these areas under terrestrial and extraterrestrial radiation curves gives us information about the total radiation intensity. How much radiation intensity is there? That will be given by the area occupied by these two curves. So that's why the areas under the terrestrial and extraterrestrial radiation curves gives us information or indicate the total radiation intensities. So that is our spectral distribution of the solar radiation. Okay.